Hey everyone, today we're going to review functions in linear equations. So if you could make sure to have these pages open in your packet, copying down the examples as we go, that will be really helpful for you as you practice the RICAS problems. So what is a function? A function is a relationship where each input has one output. So I'm just going to add that up here. So function, each input has one output. And whenever I talk about functions, I like to think of a vending machine, which I'm actually going to click on my computer. Here we go. So if we think of a vending machine and how it works, you would put your money into the machine and decide what snack you want. You press the buttons. So if I wanted smart food, I don't know what this says. Let's say it says A1. I would put in my money and I would type A1. If I type in the button A1, the only snack I should get is smart food. So we put something into the machine, we type the code, and then we get out of it a snack. Now, if I type that code A1 and I get 2 snacks, let's say I get smart food and Ruffles, that's great for me, but there's something wrong with the machine. It's not functioning, it's not working, okay? Now, one thing to know about a vending machine as well, which I'm not seeing it here, but we also know that in vending machines, you could have the same snack in multiple places. So let's say both of these top two were both smart food. So if I press A1, I'm going to get smart food out of it. It should be the only thing I get. However, if they're very low or they ran out, I could also use A2. So I would type A2, but the only thing coming out of A2 is smart food. So when you put something into the function, you should only be getting one thing out of it. However, you could get that same thing out of the function multiple times. And I'm going to show you what I mean by that in some of these examples. Okay. So, sorry, let me just pull my packet back up. Here we go. Okay. So we input it into a rule and then we get some output. So these are some example of functions. So I just want to add the note, as I said, that outputs can have multiple inputs. Okay. And then there are different types of functions. Our main focus this year was linear functions, but functions can also be nonlinear. So linear means that it is a straight line when you see it graphed. So if we were looking at nonlinear, it would be curved like this, or it would be jagged, such as like a V. Okay. In a linear table, the function would have a constant rate of change when simplified, so it would be increasing by the same amount or same ratio on both sides. When it's not constant, it would be nonlinear. In equation form, you're going to notice that it's easier to tell with nonlinear equations because they're going to have exponents. They could also have fractions where x is in the denominator. If x is in the numerator, so if we made this y equals x over 2, numerator, as long as it's just x, then it could be, or 3x, I mean, that doesn't matter. As long as it doesn't have an exponent is the main thing. Then it is linear. If it's in the denominator, it would not be linear. Or if you had absolute value, it would not be linear. Or if you had a square root or a cube root, it would not be linear. Okay, so we have slope-intercept form. This last form is what we call standard form. So in these forms, it is linear. In any of these forms, it would be nonlinear. Still a function, just not linear. So in these examples below, we're going to circle the functions. It doesn't matter if it's linear or not, just circling the functions. And then we're going to determine if it is a function, if it's linear or not. So when we're looking at graphs, we look at the vertical line test. So vertical line is up and down. So if I sketch vertical lines through my graph, if it only passes once, that means it only has the x value is only being used one time, so it is a function. So this is a function, okay? It passes the vertical line test. However, it is a nonlinear function because it's not a straight line. It looks like a U. This is an example of a mapping diagram. So what we should find in a mapping diagram is that all the input, each input only has one arrow going to an output. Now you will notice in this example, and they will give you examples like this to try to trick you, that each arrow from each number is pointing to 4. It doesn't matter. If I go back to my vending machine, that's like saying I could press 1, 2, 3, or 4, any of those buttons, and get out that same snack, whatever 4 is. This is a function. We can't tell if it's linear or not from this, but we can say it is a function. Okay. So let's go ahead and look at this mapping diagram. So I've got 1 going to -1, 3 going to 4, 5 going to 4, and 7 going to 6. So once again, 3 and 5 are both going to 4. So that's okay. It doesn't matter. It's the fact that each of these numbers or input values are being used once. So this is a function. Let's go ahead and look at these ordered pairs. So with ordered pairs, we're going to check to see if x is used once or multiple times. So 0, 3, -3, and 2. So this is a function because each x value is used one time. So once again, we come to a graph and I'm going to see if it is a function. So if I kind of sketch vertical lines through it, I would see it only hits the graph one time each time. That is a function, and we would say it is linear. It is a continuous straight line. Looking at this next mapping diagram, 0 is going to both 6 and -6. Those are two different numbers. So right away, I know this is not a function. That's like pressing 0 on a vending machine and then getting out two different snacks. So this is not a function. This set of ordered pairs here, we have 1, -2, -1, and 1. So notice that it's being repeated, but I have -2 and 3. It has two different outputs. That is not a function. So down here, if I use the vertical line test, it's only hitting once. So this is a function. Now this one stumps people a lot. This is considered a nonlinear function. Even though it is made using straight lines, it's not a continuous straight line. You can see how this line is continuing to go in the same direction either way, whereas this changes directions at this point. So this is considered nonlinear, but it is a function. All right, so with tables, we have to see if any of the x values repeat. So -2, 1, 0, 1, 2, 3, 4. So this is a function. So now I have to see what the rate of change is to see if it's linear or not. So this is increasing by 2, while this is increasing by 1, plus 2, plus 1, plus 2, plus 1, plus 2, plus 1. So this looks like it is going to be linear. It has the same rate of change, same ratio as I go through. So we would say this would be linear. So this graph does not pass the vertical line test in multiple places. In the place I drew my first vertical line, notice it's hitting twice. That means this x value of 1 has two different outputs or two different y values. This is not a function. All right. So we have 4, 1, 0, 1, 4, 9, and 16. So 4, -. So we have the same x value, but we have to check that the y value is the same or different. So 4 and -2, and then we have 4 and +2, not the same. 1 and -1, 1 and 1, not the same. So it looks like this is a function. But is it a linear function. So plus 1 plus 3 plus 1 plus 1. So right here, I don't really need to go any further. This is not going to be linear. 1 to 3 and then 1 to 1. That's not going to be linear. It's not the same rate of change. So this is non-linear. So with tables and graphs and equations, you should be able to tell whether they're linear or not. Ordered pairs and mapping diagrams, you can't, but you should be able to say if it's a function or not. Okay. So now we are going to dive into our linear functions a little bit more, looking at slope-intercept form. So slope-intercept form is a way to represent linear functions or linear equations. It's the same thing. So in slope-intercept form, we use the formula y equals mx plus b, where m is the slope and b is the y-intercept. So slope is how your function is changing over time, how it's moving over time. Your y-intercept is where your function crosses the y-axis. So if you're looking at a graph right here, this point right here would be the y-intercept where x is 0, and your y-intercept would be b. That's what they use in the equation, some number. And then your slope is how it's changing over time, also known as rise over run. So in this word problem, Andrew orders shirts for $6.50 each with a $12 shipping fee. So y equals, so the one-time charge, your $12 shipping fee, is where you would start. Doesn't matter how many shirts you buy, you're going to pay $12. So before you even start ordering shirts, your price starts out at $12. So that would be your y-intercept. How it changes over time, how your price continues to increase, would be by $6.50 per shirt. So this is my slope, how my cost would change over time, and this would be my y-intercept. This is where your cost starts. This is where it would start on the y-axis. So if you're trying to write an equation in slope-intercept form from a graph, you need the slope and the y-intercept. So y equals, so I always like to start by finding the y-intercept if it's on the graph. So in this case, it is right here at -5. So I know it's going to be -5. So now I just need to find the slope. So slope is rise over run. It's your rate of change of y, rate of change of x. So from here to my next point on the graph, I'm going up 1, 2, 3. Remember, we always read from left to right. So we're going to go up first, and then we're going to go to the right. You can work backwards if necessary, but I don't advise it when you're trying to, if you can avoid it. So this has a slope of 3 over 1, which is just 3. So that would be in front of x. Okay? Now, and that slope keeps moving to my next point. So if I go up 1, 2, 3 over 1, there's another point. It doesn't matter what points you use to find slope. I could have even used this bottom one and this one right here. I would have gone up 6 and over 2, but that simplifies to be 3 over 1 or 3. So that slope is the same on your graph if it's linear, okay? No matter what 2 points you use. When you're trying to find the equation for a table, same thing, you still need slope and y-intercept. So if I start by looking for y-intercept, I need to look where x is 0. In this example, they did give me the y-intercept. X is 0 here, so that means the y-intercept is 2. So now I need to figure out what the slope is. You only need 2 points, and it doesn't matter what 2 points you use. I'm just going to use the bottom 2. I like to try to use small positive numbers if possible. So from here to here, I'm subtracting 0.5 or a half. And here, it's increasing by 1. So slope is the change of y over the change of x. So that would be negative 0.5 over 1, which is negative 0.5 or negative 1/2. Doesn't really matter what you use. Typically, we use fractions in slope-intercept form because when we're graphing, it's easier to use a fraction. With rise over run, it doesn't really matter. I am going to use the fraction, but either would be correct. Now, how do you do this if you don't have the y-intercept? I just want to point out or remind you there are examples already worked out here for you to look through, and I'm actually going to go through the problem. So we have to use what we know. So we know that slope-intercept form is y equals mx plus b. We can find the slope. So I'm just going to use the first 2 points. So the slope is 4 over 2, which is equal to 2. So y equals 2x plus b. Now, all of these ordered pairs work specifically for this function. That means if I was to graph this line or graph these points, they would all be on the same line. So what I can do is substitute any of the ordered pairs from this table into my equation and use it to help me solve for b. Doesn't matter which point you use, they're all on the same line. I'm going to use 5 and 13 because those are my smaller numbers. So we're going to change y to be 13. We're going to keep the 2 because that's our slope. We're going to change x to be 5, and then we're leaving b because we don't know what it is. So all I've done is replaced x and y with one of my ordered pairs, and it doesn't matter which ordered pair. Once again, I just used the first one. So 13 equals 10 plus b. If I subtract 10 from both sides, 3 equals b. So that means I have a y-intercept of 3. So y equals 2x plus 3. Now another way you could do this is you could keep the pattern going backwards until you hit 0. It's not always easy to do in a table. This way algebraically works every time. But if I worked backwards, so minus 2 would get me to 3, and then I would get minus 4 would be 9. I could see how I could keep going backwards until I got here. Little trickier, but it is possible. This way works every time. So this covers most of what you need to know. And remember, when working with slope-intercept